have this honor to speak in front of this learned group. And I have the audacity to pick up this title for my talk. And I've already changed the orientation here because I'm a little bit more dynamic and interactive during this process. So what I'm going to talk about is it's a potpourri of some things that we are doing lately on modeling, analysis, and simulation of non-stationary processes, as well as non-linear systems. And the theme of the talk is more given by this English poem, which I tinkered a little bit. And it is something old, something new, something borrowed, and something fresh. So that's what you're going to have in the next half an hour. The prevailing school of thought is that we tacitly assume that everything is linear and stationary or homogeneous, but most of the things in the real world are non-linear, that results in non-Gaussianity, as well as non-stationary and non-homogeneous. Even our financial world have just realized that the times for the bell curve are gone, and we need to look for long tails, black swans, and extremist thumb. So this is an article from Financial Times. So I think it's appropriate time that we should also jump into this more rigorously than we have, looking at these two effects. Why do we need to do that? Those days are gone when we used to have very conventional buildings. Well, we started with these in Italy, then Chicago gave us this, and then we have Burj Dubai, and while we speak, this building is being designed, and Burj Dubai is at about this level. Our experience dealing with some of these buildings are that old linear theories don't work, and if you miss, you can miss something very easily in their design needs. If you look at some of the other transient and non-Gaussian events, tornadoes are trying to approach cities, and we have a lot of experience with hurricanes attacking some of the large metropolitan areas along the coast. This is what primarily results, and it happened, this thing happened in 1984 in Alicia and Houston, and again, last year, the same thing was repeated. So, and this is Hong Kong, this is a tornado in Dallas. And some of the cladding goes, and along with that, many things get sucked out. In case of bridges, the bridges are getting longer, and we are hoping for Messina Strait Bridge to come up soon, and Sutong Bridge in China is the longest span. Cable stayed bridge. Once the bridges get that long, the linear theories do not work. And as you will see later, if we use linear theory, we will be surprised how the behavior could be changed once we include the non-linearity, resulting from either turbulence or because the angle of attack, which creates non-linearity. In the offshore area, if you look at, we have deep platforms in search of oil. And here is an example of that Chevron's TLP named Typhoon, and you can see this is what happened afterwards because somebody clipped one of the cables, and that resulted in Hurricane Rita. So these types of structures also have a lot of challenge, and as you can see, windmills are becoming very popular now. The size is almost a 747, and we have inside the buildings also some of the turbines included. And in case of turbulence, once again, the stationarity of winds, because the power changes with that, as well as non-linearity because of the turbulence, the performance of the windmill is affected. If you look at some of the non-stationary effects, you will see these are some of the storms which in the past have been ignored. We like to have static winds in a boundary layer, but these are gust fronts which dominate most of the design wind conditions in the United States and other parts of the world. Their profile is different, and if we design it according to regular, you would be missing, as you can see, cold air comes down, gushes, and this gust front has quite different characteristics, and it's very transient also. We all used to do having 10-minute average, half an hour average, 1 hour average, but in these storms, they're non-stationary, very small. So now the current thinking is that it should have a variable averaging interval, and that should not be determined by me or you. The data itself should determine it. The memory in the data, the scales present in there, and there are certain techniques which we are looking at and trying to come up with some of the more comprehensive way to do that. Here are some examples from a hurricane and from a gust front. As you can see, Nobody inserted anything here. Let the technology decide how much is the averaging interval we are going to use, and you can see the gust factor, which is the peak over static value over that, steady value over that period. And you can see that in case of hurricanes, we get larger values as compared to what we see in case of a gust front. How do we analyze these things? Because as we are getting into more complicated things, non-linear and non-stationary, our good old friend Fourier transform, which has really done great for us, is not possible to work with that. Because if I have a time series whose frequency changes with time, a Fourier transform is going to give me this. It won't tell me what is happening in there. Then of course we have short time Fourier transform, but the windows are fixed. Then you can see this stepped action. But wavelet transform, a very sound mathematical basis, provides us the way it shows how with time the frequency is evolving in there. A little bit more complicated. If whenever you take a wavelet transform, just like power spectral density, we get something which is called scaleogram. Here is a signal whose frequency is also changing with time. Here is a wavelet transform of that. And this is a three-dimensional structure. And normally what you see when you run MATLAB code, this is what you will see. And some of the people who don't believe much in wavelets because their own methods would criticize there's a lot of bleeding in here. But I think if you just rely on MATLAB code to tell you what it's going to do, you will have trouble. We have come up with what we call wavelet instantaneous frequency spectrum, which gives you crisp change in frequency. And what you do is you have to identify the ridges on that scaleogram, which helps to provide that. Again, you can take a slice here that will give you an instantaneous spectra. And those system identification people, you could always not only find the instantaneous frequency, but also the bandwidth, which will also provide you some information on the damping value in the system. Here is a case of a signal from a response of a tower, and if you do random decrement method, you will see there are some oscillations in there. You cannot get a reliable analysis of damping from this. So what you have to do is, one way to do is, take a wavelet transform and pick up the frequency at which you want to find the damping. And here is a resulting decrement. As you can see, there are no waviness in there. Then you can go with Hilbert transform to get your frequency and the damping value. Here is another example. Those of you from the United States are very familiar with this particular building in Boston. It lost a lot of glass. It was a very poor design building. The lateral frequency and the torsional frequency are almost the same. As you can see, here is a time history when the building really experienced very large acceleration. We have used this particular technique, and as you can see, each color code gives you the box here, and as you can see, the frequencies are changing with time, as well as at this particular place, both the lateral and the torsional frequencies are quelled together into one value, and in the variations this way, using the wavelet transform, we can pick up it's not possible by any other technique. Earthquake example, here is the Northwich earthquake for Sherman Oaks building. If you can see, this is the time history measured in the building from accelerometer. And as you can see, this is the scaleogram, the top view again, and you have these frequencies are present all along the time period. Then here is something, second mode and third mode. Power spectral density will give you first, second, and third mode. And let's zoom in on this particular one a little bit more. And we are now using, instead of that scaleogram from MATLAB, we're using our VIF, which gives you much crisper description of what is happening or the energy content in the signal. And now if you expand them, and you will see that this is the first mode, the building after a little while softens, then gets a little bit engaged again, gets a little bit more harder. Second mode, it softens, stays there. Third mode, this is instantaneously some portion of time in which it is getting stiffened also. This type of analysis is possible using this particular approach. Those of you who are interested in finding that causative effect of what causes another thing, one example would be if you have a roof pressure fluctuations and you want to relate it to turbulence in the approach flow. And here is an example where we are using co-scalograms. In fact, you have two signals, just like cross spectra, there's a comparable co-scalogram. And in one of this particular record of wind and this record of pressure are correlated. This one was just a phony one thrown in to see if we are getting any spurious results. And as you can see, there is some instantaneous correlation between the two. And if you use any time average scheme, you will see zero correlation between them. because this thing is happening only over a short period of time. If you want to get more fancy, we have done some more work in which we could have the higher order scalograms, which would be this bicoherence in terms of wavelet domain, where you can see the nonlinear interactions as well. There is something which I found from Russia. Renko has a very interesting use of wavelets. He married wavelets with spectra, which was very useful. Here is an example of some winds in Antarctica. And as you can see, this is a long day's record. If you want to see certain frequency of events happening, well, one could just go through that, but that's not a very good science. Here, we can find out from these wavelets, which is basically the Fourier transform of wavelet coefficients, and then you draw contours, and you can see that every 5 years, there will be winds in this area, which will last for 3 days, sorry. And this type of information is very useful for energy and for other types of use. So this can be used, a combination of spectra as well as wavelets. So we measure building responses in real world, full-scale monitoring. When we do experiment in the lab, everything is very nice. But when you're looking at very tall building in, say, Chicago or Dubai, you see results like this. You don't see steady vibration because there was a dust comes and it excites the structure. So the conventional analysis tools are not possible to give us any useful results. And so we end up using more advanced techniques. And one of them is that we take our co-scalogram and try to use SVD, and if that helps us to make things clean up, then we can go through another transformation also to isolate some of the noise issues, and then we are left with something like this, which gives us both time and frequency domain tools available to us to do further analysis in this short period. For example, you could use Hilbert transform, or you could use half-hour bandwidth, or you could use spectral moments, which could be a little risky, because your moment plots will not be that smooth. And here is another one which is very recent, surrogate data. Many times when you're doing this test for non-stationarity or test for non-linearity, things are become very complicated. It's difficult to make a decision. This is first arrangement test and others. And I think I like non-stationary test using, in which case you look for a surrogate signal. What a surrogate signal is, for example, if you have a non-stationary process, you take a Fourier transform and change the phase to a uniformly distributed phase. The spectra would still remain the same because you didn't touch the amplitude, but now you have a stationary signal. So some comparison between your original signal with its surrogate and looking at the global and the instantaneous features of that, you can come up with the null hypothesis. Like in this case, we failed because it's non-stationary. In this case, we have a surrogate signal, which is a stationary signal, and it passes the test. Simulation tools, we have a lot of experience, many of you have done, and Professor Shinozuka gave us this technique, spectral methods, and for stationary it is fine, but non-stationary, we have to look for additional tools like multiple windows or evolutionary power spectral density. But I think I'm going to focus more on using time frequency domain approach, which is using wavelets, because wavelets takes care of both amplitude modulation, frequency modulation, as well as a combination of two, which can be the worst possible scenario. Here is an example of a gust front, which is these are the time histories recorded in a storm, and this is the actual measurements. Here are the time variable mean values, and here are our simulation. I don't have time to go into the details, but there's a paper right after this session where I'll be talking more about that. Our simulation is good because you cannot just say that, oh, these look like that. They look pretty good, but you have to do some statistical tests also. So here is the measured Hilbert transform, and here is the simulated one. And as you can see, there's pretty good comparison. We also look at the cross scalograms of data. Here is measured, and here is simulated one. And we also said beyond that to say, look at the complexity of our signal. So our simulated one and the target one, we're using renaissance